Hi everybody, this is the Good Math Guys, Mike and Sean, back at you with a video I think you're going to like a lot today called Lattice Multiplication. It's the fourth one in the series of different multiplication strategies for multi-digit numbers that we've shown you thus far. The lattice requires students to be able to do certain things like draw squares and rectangles. They don't have to be perfect. You'll notice if you're looking at mine here that I prepared before starting this video. We just need to know when we have to draw them. So let's take a look at the problem that we've been doing in the past shows that we've done on multi-digit multiplication, which was 24 times 32. When the number of digits in the multiplicand, that's the 24, and the multiplier, that's the 32, are the same, we draw a square. It doesn't have to be perfect, just needs to be as close to a square as the kids can possibly do. However, when the number of digits in the multiplicand is greater than the number of digits in the multiplier, we have to draw a rectangle to account for that difference. You'll understand why in a minute as we actually get into the lattice strategy for doing multi-digit multiplication problems. So that being said, let's get at that. Lattice multiplication, and what we're going to do is the same problem that we've been doing all along, so that when I do the connections program for you, you'll be able to see how all four of these methods are connected to one another. So let's do 24 times 32. Again, in each of these factors, the multiplicand, we have two digits, and in the bottom factor, the multiplier, we have two digits. So what we're going to do is go over here to the right, and we're going to draw a square. And again, does not have to be perfect, just should, as closely as possible, resemble a square. The 24, or the multiplicand of any one of these problems, resides at the top of our square or our figure. So we're going to put 2, 4. The multiplier lives down the right-hand side, and this is a very important move, 32. We want it on the right-hand side, not the left-hand side, and you'll understand why in a very short while. What we're going to do is complete this lattice design, and we do that by creating a vertical line between the 2 and the 4, giving each its own column, and we create a horizontal line between the 3 and the 2, giving each of those digits its own row. So what we've done is we've created 4 smaller squares within our original square. And what we're going to do now, which is the last move that creates the actual lattice design, we're going to draw diagonals from the lower left to the upper right. Now, I know the kids know there's another diagonal there that goes from lower right to upper left, but we do not want to do that one. Again, you'll understand very shortly the reason for that. So it's lower left to upper right, lower left to upper right, lower left to upper right, and there's our lattice. What we're going to do now is simple grid multiplication. We're going to take this 3, multiply it that times that 4, and write response in each of these triangles. So 3 times 4 is 12, so we record 1, 2. 3 times 2 is 6. Now that gives us a single digit response. So 3 times 2 equals 6. To make sure that we put that in the correct triangle, what we're going to do is record it as 0, 6. Now, everybody knows that 0, 6 is the same value as 6. 6 becomes a placeholder here, and what it does is it forces the 6 down into the correct triangle. So any single-digit response, I'm going to precede that with a 0, so this gets recorded as 0, 6. Then we go down and we multiply the 2 times the 4, and then the 2 times the 2. 2 times 4 is 0, 8. and 2 times 2 is 0, 4. Now we're done with these numbers altogether. Here's the difference between place value in both of these models. Over here, you'll notice that place value was vertical. In other words, this was 1's place, this was 10's place. Here, in this model, place value runs at a diagonal, not a vertical. So if I were to extend this line straight out, and if I were to extend this line straight out, and once I show kids how to do this, I really don't expect them to do this, but just to help them understand, this diagonal right here would be 1's place. If I were to extend this line out, this diagonal would be 10's place. If I were to extend this diagonal out, this would be 100's place. And if I were to extend this diagonal out, this would be 1,000's place. So 1's, 10's, 100's, 1,000's, and you'll see they're not vertical like we were over here. They're on a diagonal. And again, I don't expect the kids to do this maybe once or twice until they fully understand that we're on a diagonal there. Okay, all we do now is focus on the numbers that are inside our original square to get our total product. So we're going to go to the 1's, and notice that the only thing we have in 1's is an 8. There's nothing to add it to, so we bring it down. Then we're going to go to 10's. We notice there's a 2 and a 4, so 2 plus 4 is 6. We bring it down. Then we go to 100's. We notice there's a 1 and a 6. 1 plus 6 is 7. And we add it to the left-hand side of our lattice grid. And what we do now is we read the answer for the full product down and to the right. So the answer to this multiplication problem is 768. So over here I would record 768, which is what we got when we did these models. For the most part, when I was teaching in a classroom, a good 10 to 15% of the kids that saw this loved it enough to take it on to middle school with them, and that's one of the reasons why Sean and I have decided to go ahead and share this particular method with you. We both subscribe to the idea that of the 4 methods that we've shown you, if you have a student that finds one that they like better than any of the others, then our position is that they should be allowed to gravitate into the method that most suits their particular needs as a learner of math. That being said, again, the next program will focus on making connections to all of these to show you how they're actually connected mathematically. But for now, this program will do it, and we look forward to the next one. This is Good Math Guys saying bye-bye.